So we introduce the timing diagram. We know that certain things have to happen on both sides, use the control signals, and also use the actual address of data to communicate. Use the address bus and data bus to communicate. We have different roles in such communications. We have an actor, which is also called a master. A master initiates and servant respond. We have these two roles in general. And we have directions of the transfer. The one sending data out is called the sender, and the recipient is called receiver. We have addresses, and also we expect to have data being read or write. We can use addresses to specify location in memory, a peripheral, or a register within a peripheral. Now, for some cases, if we do not have a lot of wires, we may have to reuse the wire for different purposes. This is a good example of time multiplexing. The goal is to share a single set of wires for multiple pieces of data. What we're seeing here is a master actor and a servant actor. And we are trying to send data from one side to the other side. However, the data bus is only 8-bit, whereas the data itself is 16-bit. So we really have to do something to successfully transfer all the 16-bit to the servant from the master using this 8-bit bus. And we have no other choice other than sending the data in 2 chunks. So that's why you see we have to break data into 2 chunks, 15-bit bits to 8th bit, and then 7th bit to 0th bit. You need to get used to the numbering. We always number the lowest bit or least significant bit as bit 0. So that's why the most significant bit of the 16-bit number is going to be bit 15. So in this case, we reuse the data bus and be able to transfer more bytes by sending the longer word multiple times. And the other case that we see on the right side is, apologize for that, is to transfer both address and data. The example on the left side, we are not dealing with any address because there's only one storage or run register on the servant. Whereas in this case, we have you can imagine a more complex device. You have larger storage space, which has to be accessed using an address. So in such a case, we have to send both address and data. And again, we have a much narrower bus than the actual data width and the size of the address. So what we have to do is to break the address and data transfer into separate transactions. First, we'll transfer address. So that's the first one. And then the second cycle or transaction, we will transfer the actual data. So this is called address bus multiplexing. Next, we're going to look at some basic protocol concepts or how the master controls the transfer. So the first example is what we call Strobe Protocol. It's rather simple. We have a master and a servant, and the master is going to request some data from the servant. So that you can see there's a control signal request going from the master to the servant. And we have a data bus, and that is one unidirectional, going from the servant to master. So this is a read operation. So we're going to use this following timing diagram to describe the operation, to describe such a protocol. So we'll first, the master will raise this request signal from 0 to 1, to indicating there's a request for the servant to transfer data. And then after some time, as we indicated here, t-axis, after this amount of time, we expect the servant to put the valid data on the data bus. And that's step number 2. And the third step is that here, but between the second and third moment, we expect the master to perform the read operation. Because after this moment 2, we know the valid data is available on the data bus. So the master will be reading the data during this time frame. And after the reading is completed, master will deassert the request signal and then finishing up the transaction. And for the servant, once it sees the request signal is lowered back to voltage 0, let's say, it knows that the master has finished reading, so it will stop putting the data on the bus. So that's why you see at this step number 4, servant finished sending out the data, and it's ready for the next request. So really, there's no complicated communication, because everybody is agreed upon this t-axis time. That's why when you read the timing diagrams in datasheet, you will need to pay attention to this t-axis time when you have 2 components put onto the same circuit. You want to make sure that the t-axis time is followed if this protocol is such a strobe type of protocol. The one on the right side is a little bit complicated. We call it Handshake Protocol. Physically, you can see that we have one more signal. We have a ACK, which stands for acknowledgement. Still, we are transferring data from the servant to master, and the master initiates such transaction. The first step, the master will assert the request signal, as we did in the Strobe protocol. And the second step, the servant puts data bus and assert ACK. Now, this asserting of the ACK is important if the servant cannot guarantee such a t-axis time. The t-axis, as we see in the earlier this Strobe protocol, this is agreed upon on both sides. But if there's no such t-axis time, so this could be a variable. This could be long, could be short. That means the servant could take longer to put the data, valid data on the bus, or take shorter time. So with this ACK coming from the servant and going into the master, the servant can say, hey, master, when you see my asserting this ACK, you know that my data is valid. So that's why you see that this data is slightly, the valid data is earlier than the ACK is asserted, which is reasonable because the servant has to make sure the data is valid on the bus before it actually asserts this ACK signal. The master will look at the ACK. It will not read until it sees the ACK. So during this time frame, between this point and somewhere this point, so this is the moment the master will read the data. Because from reading the ACK, which is asserted now, that's a logic high, we know the master knows that the data on the data bus is valid, so it's safe to read. And after reading the data, the master will deassert the request, indicating that the data has been read, and then this servant will respond by deasserting this ACK and also deasserting the data. So the servant is ready for the next request. The next one is a combination of both. We can say there's a compromise, and physically we have a request signal, we have a wait signal, and we have data. Okay, the story is the same, or the goal is the same. The master is trying to read data from the servant. In a fast response case, as we show here, there's no involvement of this wait signal. So the wait signal is always deasserted, so it's 0 all the time. So this becomes a typical Strobe protocol. So the master requests the data after T access time, putting the data, valid data on the bus, and then master reads during this time frame, and then master deasserts the request, and then finish the transaction. So in this case, the wait line is unused because the servant is working as expected, is able to put on the valid data on the data bus within this T access time. But in some other situations, maybe the servant has to wait for other events to happen, or some internal faults causing delays. So after this T access time, it does not expect to produce the valid data. So if we follow still the first protocol here, then the master would try to read data on the data bus, which is invalid at this point, because you can see here the data is invalid during this time frame. So that's not safe for the master to read. And the servant needs to use wait signal to notify the master of such case. So it will, in the second step, assert this wait signal. This is indicating, this is to indicate that the servant is slow producing a valid data. And this wait signal is asserted, which will be seen by master because it's all connected. So the master sees this signal goes from 0 to 1. It knows that the servant is not ready, so it will not read. Okay, so when we move on further, at some point the servant has valid data, which is here. So this you can expect a uncertain amount of time. But servant itself knows when the data is valid, and after that, it will deassert wait signal, okay, which is seen by the master again. So the master will go ahead, start reading, which is somewhere here during this time frame. Once it finishes reading, it will deassert the request, notifying the servant that this transaction is done. So this kind of design is very useful for the case when the servant is slow in responding. So with these two control signals and this Strobe handshake compromise protocol, we can handle both fast response case and slow response case. Okay, next we're going to talk about I/O addressing. I/O addressing is for the microprocessor to communicate with other devices using some of its pins. And we're going to be looking at port-based and bus-based. So port-based I/O or parallel I/O is when the processor has one or more n-bit ports. Many processors, for example, PIC microcontroller, some of Atmel microcontroller has ports with names. And when you access such ports, this is still on inside the microcontroller. You can use the names of the port. And the software reads and writes a port just like a register. for example, you can say port 0, assign a value FF to that port, or you can get the second bit of port 1, get a value and assign to V. So this is something you can use if that microcontroller or processor supports C language, which is most of the case. The other way to access the ports is to use bus. When we talk about bus, we are talking about addresses and data and the control signals. We can use these buses to form to read a bus-based I/O device, I/O port. The communication protocol is built into the controller. You really don't have to use the software to emulate the timing diagrams. Most of the time, you will just use the address and use the data, and you should be able to get the data correctly, provided that your microcontroller is connected to other components following the timing diagram. And in such case, from the software perspective, you can use a single instruction to carry out read and write operations. There are some extensions of such a design. For example, you can use parallel I/O peripheral. If your processor supports only bus-based, that means the processor itself will need to have an address bus and data bus to access other components. If you really have to have these, ports, parallel I/O peripherals, you can attach that to the bus. So this will be a secondary controller. You will be able to read and write the registers here, and then subsequently access these port A, B, C. The other one is extended parallel I/O, where you have these ports which you can access using their names, as opposed to using the addresses. You can do that, but also you can extend this using a parallel I/O peripheral. Then from this port, you can access registers here, and then from that, you can access other ports. Memory mapped I/O and standard I/O. So this is when we connect the microprocessor, microcontroller to I/O devices. Like we will do in our second lab, we will connect the Arduino to a I2C device. So that's another peripheral or device that you will access. For that, we have two options. For this kind of situation, we have two options. One is use memory mapped I/O, one is using standard I/O, and depending on which processor you choose to use, and also the internal architectures of the processor. For memory mapped I/O, you treat these I/O devices as another memory location. If you recall, I think last week, we have shown you a memory map about the microblades processor, and it has a memory map. And so those segments of memory, some of them are used to access particular I/O devices. Standard I/O is where you have dedicated memory I/O pin to say what is the memory access, what is the I/O access, and that will be used to differentiate memory access and the I/O access. For memory mapped I/O, you don't need any special instructions. Everything is treated as a memory address, so you don't really know what you're accessing unless you specify the address and also the resources on that address. Standard I/O, where you will not use a general memory address, you will use I/O instructions to access a specific I/O device. Okay, so here we are looking at a very basic memory protocol. Let me explain a little bit. So we have, so let's start from here. This is the 8051. This is a microcontroller, very popular. You can see all, many of such microcontrollers in the field. And this microcontroller has several ports and also several pins. So P0, you can think about this as the named port. So you can access the 8-bit port. So you can access the values on these 8 pins using the name of this P0, this port. Similarly, you have a port P2. Again, you have 8 bits here. Besides those, we have a few control signals, ALE, address latch enable, write control, read control. This is the, I think, another enable signal. So what we're trying to do is we want to use this microcontroller to access these 2 memory chips. One of them is, I think it's ROM, this is a read-only, and the other one is a RAM, so you can write to this memory chip. But you don't have to worry about the actual chip itself. What I want to show you here is to access these components, you will need to use address, which is here, A. Okay. So for these two memory chips, you all need to use address, and both of them needs 16-bit address. And when you access these memory chips, for the case of ROM, so it's read-only. So you provide the address, and you expect to get data out. So we have 8-bit data out. Okay, and these data bits, 8-bit data will be read to the microcontroller to do some computation. And for this RAM chip, you can both read and write. So depends on the operation, you might read data from memory to the processor, or write data from the processor to the memory. Either way, you need to use these addresses. Now, here's the problem. What is the problem? The problem is for addressing either one of them, you need to have 16-bit address. So if you use P0 alone, you cannot provide 16-bit address. Same case here. If you use P2 alone, you cannot provide 16-bit address. So that's the problem. So the solution here is to use this 74373. This is a latch. Latch is an IC that can basically store the value that you put in. So if you put a value here, 1, and if you give a pulse on this ALE, on this G signal, you will be able to pass the value from the D side to Q side. So this chip will be able to store whatever value you put on the D and reflect on the Q until you next time update this value here. So that gives us a chance to basically store parts of the address, specifically to store 8-bit of address using this Q, and provide the other 8-bit of the address on the other port. And this is exactly what we're doing using this protocol here. We have first P0, let's see, yeah, P0, we store the lowest 8-bit of the address. So address bit 7 through 0, and P2 stores the higher half of the address, so bit 15 to 8. So the address will be put onto these 2 ports at the same time. And then we see that at some point this ALE is asserted. So you have a pulse here. And because you present the lower half of the address to the D side, so this latch will respond to that. As a result, on the Q side, on the output of the latch, you will see the lower 8-bit of the address going to be present on this side here. So what we're really doing here is this ALE will make sure that all of the 16-bit address are going to be present with a combination of this Q and this P2. So in this way, we are able to provide all 16-bit address to either one of these memory chips. And that's not the end of the story, because when you supply the memory address, you want to read data. Let's see, we're reading data from one of the address, depends on which one we select. We can select using this, right. Yeah, we can select by using this PSN here. When the data is read out of the chip, the memory chip, so it's going to be presented on this here, and that's why we perform the read operation by asserting this read. So the data is coming out, and then we will be able to see the data on the P0 port. So the data will be present here, and then the microcontroller will be able to read the 8-bit data from this P0. So this is a very interesting example, although this is probably the first time you think hard about the timing diagram to figure out what this actually does. But I think this is a good exercise for you to understand these concepts of control signals, buses, and how the timing diagrams describe the protocols.